Lesson 5-6, the remainder and factor theorems, roots and zeros. Objective, determine whether a binomial is a factor of a polynomial by using the remainder theorem. Find the zeros of a polynomial function in the set of complex numbers. Let's take a look at synthetic division. Something very surprising happens. When these are both the same problem, one done long division and one done synthetic division. And notice they both have the same remainder, -8. Now, what the remainder theorem says is that if I were to put the number 3, that divisor, into the function, look at what we get. So substituting that divisor into this function gives us our remainder. Let's take a look at the remainder theorem. Okay, this is what the remainder theorem says. If you have a polynomial and you divide it by something, you get you get the quotient and the divisor and a remainder. Let's take a look at a number example to help you out. So in this problem, I have a quadratic, and this is my divisor, this is my quotient, and here's my remainder. So this is the way the problem would have looked in a fraction form. I would have gone through synthetic division, and I would have got this answer right here. And notice that this remainder, 42, is the same as if I would have put 4 into this function right here. So we can anticipate what the remainder is before we actually do the problem. All right, let's take a look at one of the most interesting remainders, and an interesting remainder is the remainder 0. Okay, I am going to divide by x equal to 3 using synthetic division, and notice that we're getting a 0 as our remainder, which means it goes into it evenly. So what this is telling me is this cubic right here, the x plus 3 went into it evenly, and so now I'm going to take this and I'm going to translate it. This is going to be 2x squared minus 9x plus 10. And so these two multiply to make this cubic. So the remainder theorem, when it's 0, helps me to get 2 factors for the polynomial expression. Now, the factor theorem says that this is officially a factor if the remainder is 0. So if this remainder is 0, then this x plus 3 is actually a factor, and its quotient is also a factor. All right, let's take a look and determine whether x minus 5 is a factor. Now, the first thing you ought to do is, before you do synthetic division, you ought to just figure out what f of 5 is. And f of 5 is 125 minus, let's see, that's 175 plus, and then that is 5 times, that's 35 plus 15. Okay, so then this is going to be 125 plus, that's going to be a 50. So this is equal to positive 175 minus 175. All right, so the remainder theorem says we're going to get a remainder of 0. So it's worth us going through synthetic division. And we're going to get a 0 here. So how do we translate the synthetic division? Well, we have found that x minus 5 is a factor. And then here is the quotient. Let's go ahead and write it. X squared minus 2x minus 3. All right, now this is factorable, so I can continue. And this is a quadratic, x, 3, 1. I want more negatives than positives. And so this is what we call complete factoring. All right, let's go ahead and do it again. X minus 3 is a factor. You might want to try substituting before you go through this, but we can see that it did work. So we know that x minus 3 is a factor, and I'm going to translate this. X squared plus 7x plus 6, and I can see I can continue factoring because this is a quadratic. And I'm going to write plus 6 plus 1. So this is completely factored. All right, pause and see what you can do. And here's the answer. So I used the remainder theorem to verify that this was 0. And once it's 0, I know when I go through synthetic division, I'm going to get a 0 here. So I know that x plus 2 is a factor. And then I translate this over here. And then this was a quadratic that could be factored as well. So the choice is A. Okay, let's go through some vocabulary. Let's talk about these words: zero, root, factor, and x-intercept. Okay, here's a picture right here. When you have a picture of a polynomial, these things right here are called zeros. So when you're talking about the graph, those things are called zeros there. Now, when you're talking about an equation, you're not talking about the graph, and you're looking to solve for x, we call those roots. Now, roots are what x is equal to. So x can be equal to -3. Now, if I go ahead and bring the 3 to the other side, then we call this a factor. Right here, a factor. And we can do this for each one of our roots. Now, each one of these are x-intercepts, and x-intercepts have an x and a y component here. So remember, the y's are always 0. Okay, fundamental theorem of algebra. Every polynomial with degree greater than 0 has at least one root in the set of complex numbers. Let's take a look at some examples. This is a quadratic. And let's go ahead and find the roots, okay, because we're working with an equation. Or if you're looking at the graph, we're looking at the zeros. Okay, you can see that this can be factored. This is a perfect square. And there's actually 2 answers. They just happen to be the same one. And we call this a double root. Now notice that it's one real answer, but there's 2 of them. And 2 with a quadratic. Let's take a look at this problem. Notice that it's a cubic. And let's go ahead and use GCF. Take the x out. And then we're going to go ahead and solve for this one. And we're going to get some imaginary numbers. And let's see how many we have. We have 0, 5i, and -5i. And we have a third degree, and we have 3 roots. Okay, and that's not an accident, because the corollary to the fundamental theorem says a polynomial of degree n has exactly n roots. This means if it's a third degree, it'll have 3 roots. Fourth degree, 4 roots. Fifth degree, 5 roots. Also, the other thing is the complex conjugate theorem, which says that if you end up having a complex number that looks like this, you will also have its conjugate. So in this particular problem, 3 plus 4i is a 0. We know that its conjugate will also be a 0. So they go along in pairs. Let's take a look at this problem. Write a polynomial with the given information, a polynomial of third degree with zeros, with these zeros. So we know that x is equal to -2, x is equal to 4, and x is equal to 5. I'm going to move this over to the other side. And these are all factors now, so I'm going to call my function x plus 2 times x minus 4 times x minus 5. Okay, now we can leave it this way, or we can multiply it out. Okay, let's go ahead and do it again. Now this is a fourth degree, and fourth degree means there's going to be 4 answers. So x is equal to 2, x is equal to -3, x is equal to I, but remember conjugates occur in pairs, so we also need its conjugate here. So this is going to be x minus 2 is equal to 0, x plus 3 is equal to 0, x minus I is equal to 0, x plus I is equal to 0. So f of x will look like this. X minus 2 times x plus 3 times x minus I times x plus I. Now in this case I am going to multiply things out. So this will be x squared plus x minus 6. This will be x squared minus I squared. So this is going to be x squared plus x minus 6. X squared, remember an I squared is -1, so this will be plus 1. And then I'm going to start multiplying out. I'm going to multiply this to all of these. So this is going to be x to the 4th plus x to the 3rd minus 6x squared. And then I'm going to distribute here, plus x squared plus x minus 6. Now I could do a little simplifying by gathering these two together, and there's the answer. Okay, your turn. And here's the answer. Your turn. And here's the answer.